Okay, hi everybody. Let's start CS109. First announcements. Some of you already asked on Piazza where the grades are for homework 2. They're getting out tonight. So if you haven't received an email yet, that's simply because we didn't send them out yet, so no need to panic. They're going to come today to your inbox. Final projects. Also, some attentive people already noticed that the proposals are coming up soon. So we're here, right? This is the schedule just from the webpage. So if you go to cs109.org and click on the schedule tab, here's the lecture schedule. And you can see we're going to talk about MapReduce today. And then on Thursday, Rahul is going to talk about Spark. You see it's about 2 more weeks, no, three, and then the final project proposals are due. And I'm emphasizing this now already because if you look at our syllabus, you're supposed to work in 3 to 4 person teams. So if you don't have a team by now, please team up. Like, you will need some time to form your team, to think about your final project topics, what you want to do. And then the way it's going to work is we're going to make a Google form, and you all can, that's going to ask for the individual team members, GitHub ID, names, all the identification stuff, and then an abstract for your final project. And the way we're going to do this is we're going to ask for these final project abstracts on Thursday, and then the TFs are going to pick the projects they find most interesting and that they want to advise. And then in the next week, you're going to meet with your TF, who's going to be there for you for the final project phase, and you're already going to get feedback. This feedback is meant to tell you things like, your project is really, really great, but way too ambitious. There is no way we think that you can make this in the restricted time frame you have. We might also tell you, well, you're 4 people, right? Maybe put a bit more in. 4 people actually can do quite interesting stuff. So this, where it says project review week, this is what we mean. You are going to be contacted by your TF, and you're going to meet with them somewhere during this week to get feedback on your final project proposals. Any other questions about the system, how this is going to work? No. Okay. I'm always really excited about the final projects because every year there's students who just come up with really cool ideas. I actually think we might have an inspiration reel maybe on Thursday or maybe in the week afterwards, so that you can see what types of projects were done in previous years. The other thing you can see, there were also questions about the topics for the final project. So you have seen classification methods, you have seen regression. We basically went through all the supervised methods you're going to see in the course. And if you look at the schedule, the things coming up still are mainly unsupervised. So there's clustering and text analysis, LDA here. So it's okay if your final project already, if you want to look a bit ahead and say, I really, really want to do this topic, that's totally fine. So you don't have to restrict your proposal to the things we discussed until today, right? So the proposals are due even after the green module here. So if you want to play it late, you can also just have a look already at LDA, right? You know it's coming up, so you're all fine to use all these topics in your final project. And this is really important to us because data scientists basically never work alone. So please team up, and we take that seriously. Next topic is coming up. So I went a bit more slowly last time than I thought I would be, so we have a bit more catching up to do on the machine learning best practices. I saw some very cool Piazza posts, though, so I'm glad that you learned from these slides, and that was maybe a good speed for you to catch up. Then we're going to talk about recommender systems, collaborative filtering and content-based filtering, and we're going to start with MapReduce today. There's a lot on our plate. So first, I summarized it a bit more, but I wanted to go back to the cross-validation because I thought it was maybe a bit confusing last time. So again, we have the 3 data sets, training data, validation data, test data. And this is the basic 5-fold cross-validation scheme. You do your 5 folds, 5 equally sized chunks of your data. You always separate one out as the test data. You train on the remaining 4 and test on the 5th, right? And then you rotate around with your 1 fold that has the test data. That's the very classic figure that you typically see in every textbook that discusses cross-validation. The point I wanted to make on top of this was that you can nest the two. So if you now also have hyperparameters to tune, the C and the gamma of your support vector machines, the number of features to split on for your random forest, what you do is inside, so this picture here basically only looks at one of these lines. So I'm talking now about only 1 fold of this 5-fold cross-validation loop. So inside this 1 fold, I have 1 chunk of test data, and these 4 chunks are my training data. What I do now is I put the test data totally aside. I take the chunk of training data that I have for this fold, and I can do cross-validation again on this training set that I have. And here I just reuse the chunks I have from before. You can make these 5 folds. You can also make these 10 folds, right? The idea basically just is set the test data of that fold aside, use the remaining training data, and now just do an inside loop, right? This is now the whole data set you have. You can again separate it into folds and do the whole thing over again. But this time then, the folds go over the validation set. So I would use this inner loop to tune the hyperparameters of my SVM. And then when you've done this, you select the best hyperparameters. And now you can use the whole chunk of training data again, train your support vector machine using these parameters and evaluate. Only in the very last step. This can give a bit more data to your training algorithm. So the idea is you take the best parameters, and best is determined by your validation set, not the test set, validation set. And then once you have that, you actually can use this chunk and put it together with your training data. That's okay, right? Because you do not touch, during training, you still do not touch the test data, which is the one you're actually going to evaluate on in the end. So that is then the final score you get. So we already talked about that you need to make sure how to aggregate your parameters, and that you need to make sure if your hyperparameters are jumping all over the place, right, that is most probably an indication that the data chunk is too small, right, that you're evaluating on not enough data, training on not enough data. What you then can do is this outer scheme here, you can use more folds. If I make this 10-fold cross-validation, that chunk here of test data gets smaller, and I have more data to train and to tune my hyperparameters. You're going to pay in computation time for this, and in variability maybe of your results. And we said if the hyperparameters are on the border of your grid search window, if you're testing parameter t values 1, 2, 3, and 3 is the best parameter, then you go right back and also test 4 and 5. Right? Because you don't know. It might actually be that you just started to look into the valley and the actual minimum is still out there. So you want to look for it. So I have 2 scenarios here for you. And I'm not going to leave them open to discussion, but I'm going to tell you. So this describes a scenario that a lot of people do and that you can actually find in publications. It's about feature selection. And it's very tempting. What you do is you have your whole data set, and you do something, your favorite method of feature selection first, and you reduce that data set. And then you tackle the actual machine learning problem and start cross-validation to tune your support vector machine and get your results. That's wrong. Don't do that. Because you just used the whole data, including your test data, to estimate the best features. The correct way to do this is to do feature selection for each fold. You have to do also this inside the cross-validation. Basically, if you think about your whole processing pipeline, the cross-validation part is the overall big thing that encompasses everything else. Here's just about, it's hard in cross-validation to choose folds. You can go all the way to the extreme, by the way. There is k-fold cross-validation with k equals 1, n, k equals n. So if you have only, let's say, 100 data points, you can do 100-fold cross-validation, which is called leave one out, because that's exactly what you're doing. Your test data is size 1. You use 99 samples to train, and then just one sample to predict. And you actually can do that. Here's the effect you have by reducing your data with the folds. So this is, I think, a cool figure from Hasty. So let's say you have 200 sample points, and we do 5-fold cross-validation. And this is a curve here that shows 1 minus your prediction error. So higher here is better. So we have 200 data points, and you can see the error is, not the error, the performance is up here, so it's pretty okay. And now, if I do 5-fold cross-validation, what it means is I have 160 samples to train on. So the error I'm going to get is somewhere here, which is not that big of a difference. However, if my data set already is fairly small, and let's say I only have 50 data points, if I do 5-fold cross-validation, then 40 data points compared to 50 make a big difference, which means I'm going to underestimate the performance of my classifier using cross-validation, which is fine because it's under-promise, over-deliver. The classifier is going to work probably better than what you get with your cross-validation. So, and here they show a simulated example. So in yellow, you have the actual performance here. Now it's misclassification error, so now lower is better. So in yellow, you have the actual performance, and here's the performance measured by cross-validation, including the error bars. And here you see this, right? The cross-validation estimate is significantly worse than the actual performance. But then as the subset size P here is your training data size, as that increases, the two converge to each other. And for us, the real important part is the minimum of the two here is in the same area. So that's nice. Sorry, there was a question. Yeah? Which numbers? These? Oh, if you have 200 data points and you do 5 folds, then there's 40 data points in each fold. So you have all your 200 data points, right? Do 5 sub-chunks. Then in each of these chunks, you have 40 data points. You set 40 aside for testing. You have 4 times 40 points left for your training data. That's the 160. Yeah. Okay, that's all I want to say about cross-validation. There was already a lot. But it's like, it's your major weapon against overfitting, which is your major problem when dealing with machine learning problems. So cross-validation done right, most of the time, is the key concept to actually performing well. So normalization, there's already been good discussion on Piazza. I want you to be very careful with this, because it's very easy to leak into test data when you do normalization. And you also have to think about what is a useful normalization. So most of the time, it's a good idea to center the mean. And then you have to think, should I normalize the standard deviation? Should I not? What are the units of my different features? Or maybe you just want to normalize to the range of your data. Here's an example. That's the MNIST data. That is a bunch of patches, image patches with handwritten digits in them. Doesn't matter for this example. The only thing that matters, each of the features is kind of already normalized because the values only go between 0 and 1. And this is if I perform PCA on this data and then project it down to 2 dimensions. And this makes sense to me, and I kind of nicely can see that the ones here separate out, which makes sense because there are a lot of black pixels, right? If you have an image patch and only a 1 inside, there's a lot of black going on. If I normalize the standard deviation of this data set, if I don't think what my data looks like and what I want to do with it and what I want to do with this visualization, I actually would prefer the other visualization. So by standardizing on top of the range that is already normalized, right, I kind of screwed up my visualization. So think about what normalization actually makes sense for your data. Again, know your application domain. Know what everything means. And then here are two different schemes that are both valid for normalization. One thing you can do is you can normalize each chunk by itself. Take all your training data, you estimate the mean and the standard deviation, you normalize, using the parameters only for that set. You use your validation data, again, estimate and normalize just this guy and just this guy. That's okay, there's no leakage here. There's also a problem with this. Yeah?
Quick question, please. The previous graph you showed, the axis and colors, what do they mean?
What, this axis, the colors?
Yeah, the axis and colors.
MNIST, that's just the MNIST data set. So the question was, what do the colors mean? The MNIST data set is handwritten digits. So you have the classes 0 to 9. And these are the colors for 0, 1, 2, 3, 4, 5. And then they're kind of color-coded. So if these are light blue, let's take the other one. The light blue guys here are the zeros, most probably, and the darker blue guys here are the ones. Those are the principal components, right? They don't really have a meaning by themselves. What you can do is, if you take single samples here to kind of get an idea of the axis, I have seen this for only handwritten 3s, then you can kind of see that it's an indication about how stretched the numbers or something like this. But in general, it doesn't necessarily mean that PCA gives you something meaningful. So back to the normalization. So this is fine. Yes?
In this way that you are saying that normalizing individually is trying to set, I think there's a problem because sometimes when we have the very high number of folks,
Yes.
we have a very small number of points in validation or in
Yes.
tested. So I think it's better to keep what we have in training set, the factors, and use it to normalize it the rest out.
Yeah, exactly. Thank you. That was exactly the problem I wanted to point out. Very, very good thinking. So the problem with this is, as your colleague already said, your validation and test set might be very small. The reason this is fine is you assume that all the data comes from the same distribution and that your mean estimate is correct. If that data is very large, that's okay, right? Most probably you get mean estimates that are fairly close to each other. If that is not the case, and the validation or even just the test set alone are quite small, then you get a large error on your estimation, and this might screw up your results. So what I prefer to do is I use the largest chunk of the data, which is my training data, and I use this to estimate the mean values, and then I normalize all 3 chunks using these parameters. Same goes for standard deviation, rank, whatever, rank, I keep saying rank, range. Range, whatever you want to normalize by. Basically, think about these normalization parameters as hyperparameters of your method. It also means that when you push out the classifier, let's say you program an application for biologists to use later, those values need to be stored because the new data that comes in should be treated in the same way as your test data. Other questions about the normalization? Cool. So one final, I think this is really the final thing about cross-validation and all of this. The cross-validation scheme you typically see is meant for independent samples. It doesn't matter where you grab out your data. There's a lot of applications out there where the data is not like this. For example, I work with these electron microscopy images that actually come from a volume, and we start by aligning them. So if I can segment one image very well, and then the next image is actually not looking that different, because it's one volume and they're adjacent to each other. There's a high correlation between the two. Also, just within an image, if you randomly sample, right, 10,000 points from an image, and then you randomly sample another 10,000 points. And let's say those two could even be disjunct from each other. So no overlap between your training and test data. Still, if you have an image, one pixel and the pixel directly next to it are going to be highly correlated in their values and in their characteristics, right? So that means that your data samples are actually not independent of each other. And when you do cross-validation, you need to take that into account. So it's not a good idea then to just randomly shuffle your data and separate it into test and training. What you need to do then is you need to separate these into different chunks. So what I can do typically is I take the first part of the volume, then I might even leave a gap to make sure that the start of my test data is not correlated with my training data, and then I take the last part of the volume as my test data. Your test data should simulate the person who provides your data coming to you and having a fresh chunk of data, right? And if your test and training data are correlated, whatever the person comes up with next typically is not correlated to what you got before. Does this make sense? Any questions? Cool. Again, know your application. Imbalanced data, often overlooked. I had more than one student coming to my office and saying, my machine learning algorithm doesn't work at all. And I talked to them, and within 5 minutes we figure out, oh, the problem is actually imbalanced, and they didn't account for it. So what I mean by this is, in my case, for example, the membrane pixels I look after only are 20% of the actual image. 80% is background. It's not 50-50. If you have hospital data, typically the people coming to the hospital and doing the test procedures are sick. So it's harder to have a healthy person go to the same test maybe, or also more expensive, to get samples from healthy people, right? So you end up with data sets, and you would like to use all the information in there, but one class is highly overrepresented compared to the other one. And there are few things you can do. One is you can subsample. You can reduce the majority class to the number of samples of the minority class. You can oversample the minority one, basically doing bootstrap to a size that it's the same as the other one. You can reweight sample points. I'm going to have an example for this. You can use clustering to reduce the majority class to the minority class. We're going to talk about this when we do k-means. You can recalibrate the classifier output. This is, for example, with the random forest, you have a threshold, right? How many votes do I need for one class to actually say this is this class? And typically that threshold that scikit-learn is going to give you by default is 0.5, because that is the class probability. So it's a good idea to then do a ROC curve or do a precision recall curve over this threshold and look at how this actually performs. And in my case, the threshold is always lower than 0.5. So these are different things you can do. The random forest, I think, is especially suited to illustrate one nice concept. So as I said, you can oversample, right? You can basically blow the smaller guy up. You can subsample. Now think about the random forest. We train each tree, right? And each tree is trained on a bootstrap sample. So what I can do is I can take my imbalanced data, and now I subsample this data, and I train a tree. Now I do the same. So what is going to happen with bootstrap samples of this size? I'm going to have one bootstrap sample from this guy. So this is what we have before, right? This bootstrap sample has the same size as this. But now what I'm doing is I'm reducing the size of this bootstrap sample to the size of the minority class. What is happening now is I subsample the data. Each tree sees a balanced portion of the classes. But because I sample each time from the majority class over the whole forest, I actually cover my whole data set. Right? Does that make sense? And you can generalize this with ensemble methods and basically just use this idea. Whenever you sample in your ensemble methods or also inside cross-validation, you can reduce the two, or you can also blow this guy up, reduce this guy, that they're kind of even. Yes?
So each of the small red dots are actually different?
Yes. Each of the small red dots are actually different. What I mean here are bootstrap samples. The other option you have is to reweight points. We've seen that in boosting, right? Remember in boosting you had your very weak classifier, you looked which points were misclassified, and then you adjusted the weights on those points. You basically told the classifier, pay more attention to those samples because you got those wrong, right? And then you retrained the second classifier that paid more attention to these points because they had a higher weight, got a different result, and you went on. You can do that with a powerful classifier right from the start. For example, here it's done with the support vector machine. So the solid line is done without any weights. And what you see happening here is there are a lot of blue guys here still, because blue is our majority class. So it's basically sacrificing all these red guys to get these nice blue guys all correct. Whereas when I put more weights on the red guys and say, please pay attention to those and don't do misclassification errors, right? Then I shift my decision boundary here, my hyperplane, in a way that it's taking all the red guys, or at least the majority of those, into account, because I said they're more important. That make sense? It's very similar to a bootstrap sample where you oversample, right? If I sample each point 3-4 times, it's similar to giving it a higher weight, because it's going to be counted as misclassified 4 times, if it's 4 times in your training set. But typically, if you look at the scikit-learn signatures of the functions, they have a parameter in their class weight. So that's what it's for. So, and if you do cross-validation with imbalanced data, one thing you can do is use stratified sampling for each fold. What that means is you make sure that this class imbalance is the same for each of your folds. You do not just randomly partition, right? Instead, if it's 2080, you make sure that each of your folds has this 2080. So basically subsample the classes separately. Okay, that was it about imbalanced data. Last point, which actually gets us over to the recommender systems now, is missing data. So what do we do when data is missing? With missing data, I mean you have some data points where some of the features are missing, or measurements were not done. All of a sudden, in the middle, somebody fell asleep and didn't notice the machine was actually producing errors. So there are a couple of things you can do. The easiest one is you just delete those. The incomplete samples, you just say, I don't care. I still have a nice chunk of data that is complete. I'm just going to reduce those. That's actually realistic in a lot of applications. So if you have enough data, you can just say, OK, I ignore those. I'm going to go with all the points that are complete. But there are other applications where this is occurs very often. So then if you want to throw away 80% of your data, you might rethink and say, well, can't I maybe use that information that is in there, right? It's not all missing. So one thing then, a very simple way to get values for those features is to just use the mean feature value of all the others. What I mean is, so let's say this is your data matrix X, right? And here you have your features. And then down here you have your samples, right? And then this is X1, X2, X3. And let's say this is 10, 5, and now here's the missing value 4. And this is, I don't know, 9, 2, 1, 4, 3, 8, you get the picture. So here's my missing value. What I can do is I take all the other guys here that are in there, compute their mean, and put it in here. Think about restaurant ratings. And these are different users here, and this is a particular restaurant. what I'm basically doing is saying, okay, so many people rank this restaurant very highly, so most probably this person would also like this restaurant. In a way, so it's not totally stupid to put the mean value in here in some applications. It is stupid with respect to a certain point, and that is, if you think about your sample, right, about the row here, I just destroyed any form of correlation between this value and the others here. Maybe this person here was very grumpy and actually rated all restaurants 2 points less than everybody else. I just destroyed that information for the first feature here. Yeah, it's not correlated to the rest because I didn't use the row to estimate that sample. And then we talked about regression, right? Remember k-nearest neighbors and support vector machines and all that we had last lecture. All those methods you can do regression with to query points that weren't in the data, right? You're interpolating 2 points, and then you query in between to get missing values. So this is also something you can do here. So let's talk about the application for missing data values, recommender systems. I already used it, right, with the restaurant example. So we are actually in a world by now of recommender systems. You can hardly browse the web without personalized advertisements, things recommended to you. Amazon. People who bought this also bought. Maybe you are interested in those items, right? Frequently bought together. All this is meant to provide you with information over items you might likely buy, right? Netflix. Because you like this in this movie, you might also like this movie. That was the big Netflix prize. That's also what it was about. Facebook might do, it mostly recommends games and clothing to me. But you like something, right? And immediately there's a column popping up underneath about articles that you might also want to read. All those are recommendations to you. Pandora does music recommendations for you, and Pinterest does all different kinds of things you might like based on the things you pinned before. So it's a really everyday thing that you know by now. These are the resources I used for the remainder of this lecture. I think they're both really great. One is slides, one is a tutorial, highly recommended reading. So we can treat recommender systems as a matrix completion problem. So let's think, here are the users. Right? This is a rating matrix, and here are different items that have been rated. So this user really, really liked those pictures, didn't like that book, really liked that movie, and really liked this game. And this user here didn't give you a rating for the pictures, but for all the rest. So this is the way to read this matrix. So now the question is, here's the user that is currently active, and we want to know, would this user like this movie, given that he didn't like that game, he liked that book, and he liked those pictures. And what you do then is, intuitively, like think about what you would do if you search for a recommendation. You ask your friends, right? Or strangers on the internet, but most probably your friends know you better or are more similar to you. And this similarity here is what most recommender systems try to emulate. So they try to find other users who are friend material, who are somehow similar to you. So in this case, this guy here also liked those pictures and that book and didn't like that movie. So these two ratings here are the same. So this indicates that this user here might not like that movie. Do you see what is going on? I'm just comparing the different users, thinking about who of them might be similar just based on their rankings. I'm not using any outside information here. I don't know the age, the sex, the hobbies, or anything about this user. I'm just using ratings. So this user here is similar. This user here also has two ratings in common, right? This rating here is the same for this book, and she also really liked this computer game. So, and she also didn't like that movie. So these are two indicators that this was probably means that this user will not like this movie. That's the idea behind recommender systems that use collaborative filtering. So collaborative filtering, the insight is, if Jack loves A and B, and Jill loves A, B, and C, then Jack most probably also likes C. You compare people just based on their rankings that they gave to different items. You look for those that are similar and use this similarity to try and predict the rating for another user. So as I said, you're not using any information about the users or about the items. This is in contrast to content-based filtering. In content-based filtering, you have descriptions of the items. Netflix, think about movies. You use information like, these are the actors in this movie, this is who wrote the script, this is the category, comedy, drama, something like this. You have all this information about the movies and you want to use them. I think Pandora is using this as well. They have all these descriptions of music, right? And they know that classical music is close to each other and that rock music is its own category. So they know for each song what it is like, what the speed is. They run automatic analysis and extract features from the songs to see which ones are similar. Yes?
I have a friend who works at Pandora.
Oh, cool.
Music specialist who analyze all the different characteristics of the songs, the tempos, the types of chords, types of chord progressions, all kinds of things.
So he just confirmed me. A friend works at Pandora and they do look at chords, chord progression, all of this. So these are features they extract from the songs themselves. It's not just looking at the ranking. So this is then content-based filtering. And of course, you can do also hybrid approaches. Here I just put them next to each other. So what does this imply? Collaborative filtering, content-based filtering. What happens is, if you do collaborative filtering, you might have recommendations that are actually out a bit of the comfort zone of the user. Like somebody who's only watched science fiction movies so far might also enjoy fantasy movies, because a lot of people who like science fiction movies also like fantasy movies. This switch, right, that is inferred from the other users is unlikely to be made by content-based systems, because the science fiction and the fantasy movies are fairly different with respect to a lot of features. So content-based filtering, normally you can think about the comfort zone, keeps the user in its comfort zone, right? You choose items that are similar, which for music makes a lot of sense. Collaborative filtering only uses those rankings and might hop to a totally different category if a lot of users have those in common. And of course, there are ways to combine the two. But this is sometimes confused, and I just wanted you to know collaborative filtering, only using the ranking matrix, not using on any external information. Content-based filtering, the content of the movie, the item is actually important. So, and then in collaborative filtering, there are two ways to look at this. One way is to look at, so here are basically the items then, right? I said restaurants. These can also be different books, movies that you rated, something like this. So you can either look at the rows, that is user-based, right? I'm looking for friends. I'm looking for people who are similar to me. You can also look at the columns instead and say, I'm trying to find items that were ranked similar. So in user-based collaborative filtering, as I said, you go for the rows. So the idea is that people who have similar ratings in the past will also have similar ratings in the future. And there's a problem with this that is being addressed by looking at the items, and that is called cold start problem. It's a new user coming into your system, and you don't know anything about them. And we're doing collaborative filtering, which means we have no information about that user when they first come. For most of you, most probably signing up to Netflix is so long ago that you don't remember, but they actually address this by asking you in the beginning to rank movies. So when you first sign up to Netflix, they're not going to recommend anything for you. They're going to say, oh, we have this list of 100 movies. Which of those did you like? And that is addressing this problem. They need to gather data before they can do recommendations. So in item-based collaborative filtering, it's very similar, but now I look at the number of items. And the idea here is that you have an item already for some time in your database. So it's again about the application, right? Amazon has all these items, and it's already there for a long time. And even if the user is new, the rating for that item is not going to change that much. It also might be that your matrix is highly, is skewed the right term? Basically, you have way more users than items. Right? This is also something to think about in terms of computational complexity. Which one is easier, user-based or item-based? So, and then, of course, I said this is a missing data problem. So you could, in principle, also just, again, do the mean rating of an item. I just did that as an example before. Right? You can just take the mean rating of that restaurant and say, well, that's what the person is most probably going to like. So if you want to tackle it as a regression problem, that is totally fine. You just train a predictor for each item. That was one of the strategies for missing values, right? So you train a classifier for each of those items. And each user who rated that item then basically is one of your training points, your training samples. And then you use that to predict the rating of that item for a new user. And that's good because regression is a well-known problem. So most probably we're going to do very well. One of the major drawbacks is that we train M predictors here, which is really expensive. But we know a classifier that is really, really fast to train. K-nearest neighbors, right? That guy trains in no time because it doesn't train at all. And it's actually exactly the intuition I gave you in the beginning. It's looking at the closest neighbors. So it's also very intuitive. It's looking at the other persons who rank stuff similar to me. So KNN for collaborative filtering is widely used. It can be used for item-based or user-based filtering. And you basically just do what I did before. You look at the people and how much they have in common. You rank the similarity, and you look at the k-nearest neighbors. Now, the similarity that I use so freely is the one thing where you actually need to think. Yeah, that's your bread and butter. That's where you put the meat in. I'm really bad with this. So one way to measure the similarity is Pearson correlation coefficient. It's just the correlation between two items. The problem with that is it might rank things too similar if you only have very few ratings in common. What you basically do is you throw away the missing values. You look at those that they have in common. We did this here, right? I ignored that this guy actually didn't have a rating for this. I compared this guy to this guy and said, well, two are the same, so these two are really, really similar, and I'm just going to use this rating for this guy. I did not take, when I measured the similarity, I didn't take into account that there is a missing value here. So that you can do the same thing for k-nearest neighbors. What happens then is, if this guy now would only have one rating, then a lot of people are really, really similar. Right? So it's good practice then to have a threshold and say, I'm only going to consider similarities between users who have at least n common ratings. So, and one is the Pearson correlation, the other one is more motivated by linear algebra, and that's the cosine similarity. But in the end, if you look at them, if you look at the math, they're really just the same, because here you take the product of the two vectors divided by their length, so you normalize. And if you subtract the mean of the vectors before, you have the same here, right? So I'm not going to go into the details. If you want to look at it, it boils down to the same similarity metric. So Netflix price. There was an additional thing. Remember that movie with the funny Mickey Mouse voice about Belcore and Corbell? They said that one of the big breakthroughs in the beginning was SVD, singular value decomposition. And that's the other method that is widely used in recommender systems. And they said that there was this guy, Simon Funk, who did this blog post, "Try this at home," and that helped all the other teams kickstart. And I dug out the blog post for you, and I think it's very well worth reading, not only for the method, but I really like his style, because what he did was real research. He came up with this method, he published it, so that everybody could benefit from it, and asked for input to learn more. He wasn't just after the money. He was after gaining insight and finding out what works. So this is what SVD is about. You have your ranking matrix, and you decompose that. And there's a theorem that says any real or complex valued matrix can be represented by a combination of 3 matrices: U, sigma, and T. And there are different constraints on these matrices. I'm not going to go into details about them. You can read more about this. But the idea is that you decompose this matrix into these 3. And this one here is going to be a diagonal matrix that only has entries in the diagonal. And this is going to represent users and topics, and this is going to represent movies and topics. And I found this tutorial about SVD, and it's hands down the best explanation I've seen. So of course I went and stole their example. But please, so this YouTube video is really worth your time. So here's the example, what that means. So let's say we have a rating matrix here. And these are users. Our single rows are users. And then we have the movies here, Matrix, Alien, Serenity are kind of science fiction based. And Casablanca and Amélie are more romantic based. And you can see our users here have very strong preferences. Like these guys didn't even look at the romance movies, and these guys here totally liked them and only watched very few of the sci-fi movies. So now if we do SVD of this matrix here, we get our matrix U, sigma, and V. And the way they're going to look like is this. So these are now the actual values. And what I meant by users times topics, you can see here, I get these left components here. And you can see the high values here are all in the upper part. I have users here times topics. And this topic here puts a lot of emphasis on the first 4 entries. And these are the users who really like the science fiction movies. And these here put a lot of emphasis on the lower ones. So we have 1 sci-fi topic here, basically, and 1 romance movie topic. And because we asked for 3 components, there's a 3rd one here that also focuses on the romance movies. But what you can see now in that sigma matrix is there's a high weight on the topic of the sci-fi movies. There's also a high weight on the first romance component topic. And there's a low weight on this 3rd component. So the idea here is similar to PCA, where we also got our principal components, and then the eigenvalues were ranking about how important those components are. You have the same idea here. You get your topics, and you have a ranking how important those topics are. And actually, the singular values are just, if you mean center your data before, those singular values are the square root of your eigenvalues. So it is related. You can actually use SVD to compute PCA. And a lot of the software you use is going to do that under the hood. So, but the important part is the interpretation of SVD. So you have users times topics. You have a ranking how important each topic is. And here you have the topics times the movies. That makes sense? So this movie here is a sci-fi movie, sci-fi movie, sci-fi movie, and then we have the 2 romance movies. Again, there's a high rating here, but because that is combined with this low weight, it actually doesn't count that much. So that's just an idea. There's going to be a lot more about SVD in the lab, I believe. And then the homework? No? Not? Okay. In the homework. Okay. So watch that movie. So SVD for recommender systems. So you're not only good for estimating missing data. I actually didn't go that much into the missing data point. Let me point that out. You can reconstruct that ranking matrix if you know those three matrices. So what people try to do is it's kind of a chicken and egg thing, right? If I know this matrix, I can get the decomposition. If I know the decomposition, I can reconstruct the initial ones. So what algorithms try to do, they try to find this decomposition for an incomplete A. And then you could reconstruct your A. That make sense? So, but it's not only good for doing that. We actually, on top of this, get this idea of topics that are modeled in our recommender system. Okay, wipe your slate clean. No more machine learning. I'm going to go to MapReduce now. So this is just because I thought it's very good for you to go on a high level over this before you see it in the homework and are shocked. So single value decomposition recommender systems are going to come in the next homework. And now we're going to talk about MapReduce, which I believe goes together with Spark and also in the next homework, and it's going to come back in homework 5.
Homework 4 has some MapReduce, Spark, and homework 5.
Okay. So homework 4 is going to have some of MapReduce, no Spark, and homework 5 is going to go over Spark. So different thinking. It's not machine learning more anymore. So you can put that head aside, and please take your computer scientist head, even a bit more CS205 head, and put that on. Totally different frame of mind. Let's talk about MapReduce. So what is MapReduce? MapReduce is a programming model for very large data sets. And when I say very large, I mean very large. There are some companies who say, I need MapReduce, and then you ask them, and they have stunningly 10 gigabytes of data. I would not fire up MapReduce to deal with 10 gigabytes. I do fire up MapReduce because I work with 1 petabyte of data. So sometimes companies claim they have big data, and they use these tools, but they actually don't. That's the first important thing to know about MapReduce and also Spark. So it's a programming model, and it's addressed to really large data sets. And it's a parallel and distributed algorithm. And the really nice part is it's a whole cluster framework. So supercomputers, Harvard has a really great one, Odyssey. And it's hard to maintain. Yeah? Those who take CS205 know what I'm thinking about. There's a whole lot of overhead if you have to deal with a cluster. There are all these different computer nodes, and you have to take care about all of them. In my lab, we call it babysitting the cluster. You have to make sure that no instances crash, right? You have to make them recover if they do. Sometimes instances get really slow because other users submitted jobs. Then you have to resubmit the job that run on that one instance on another one, right? All this overhead is going on the moment you need to switch from your desktop PC to a cluster. So before you do that switch, make sure it's worthwhile your time. But if you have to do that switch, it's nice if you have a framework that takes care of a lot of these things for you. And MapReduce is one of those frameworks that does the babysitting for you. But because it does that, it also is a way of thinking. It's like when you learn recursion for the first time. You go crazy until it makes click and you actually see the pattern. And that's the thing that is also going to happen with MapReduce for you. So just a bit of background, was originally developed by Google. And now Apache Hadoop is an open source implementation that is widely used out there. And there is a Python interface that is called Mr. Job. If you want to use Mr. Job, you can also, it's fine if you want to use MapReduce in your final projects, even if you don't have such big data that you would need it. I would say that's okay because you're showing that you know the method. So Mr. Job is a Python interface to Hadoop. Important, it will not run from an IPython notebook. At least I haven't found a way. So you will have to write real normal Python script, like file.py, if you want to run Mr. Job. So what is MapReduce all about? There are only 2 functions, mainly to know, and that's map and reduce. So what does that mean? This is the overall, a bit simplified architecture. MapReduce, the thinking goes in key value pairs. Everything in MapReduce is a key value pair. So you have your data coming in already in key value pairs. And then you have this mapper. And the mapper does something with the key value pairs. So the data is distributed to the different mappers. And then comes the shuffle and sort phase. And the really nice part is you program the mapper. You don't do anything here. MapReduce, the whole framework, does that for you. So your cluster internally will do a shuffle and sort and aggregate all the values by keys. So let's say the mappers here put out some keys that are letters and then some values. And this mapper here put out an A and the 1 and a 5. No, this mapper here put out A1 and this mapper maybe put out A5. And then during the shuffle and sort, it's all sorted according to the key. The key was the letter. And then it knows, okay, this produced A1 and this produced A5. So after the shuffle and sort, I get one list sorted by key A and all the values that were associated with that key, which were 1 and 5. So now I have them together here. And this then goes to the reduce, which you again have to implement. And let's say here, for example, the reduce is just sum up all the values of A, and then it's a 6. Does that make sense, the diagram? That's the whole idea of MapReduce. Already now here, a word of caution. Every time a key value pair here leaves a mapper, and during the shuffle and sort, it's written to disk. MapReduce is not very efficient with I/O. The more key value pairs you generate, the more communication overhead you have. So this is the hello world of MapReduce. It's also going to be the hello world of Spark, I assume. That's the word count example. So that's the example you're going to see in all the books about MapReduce first. So as I said, you have to program this mapping, this mapper, and this reduce step. So this is exactly what we're doing here in this Mr. Job framework. So Mr. Job works by giving you a class called Mr. Job, and what you do is you inherit from that class. So now we do Mr. Word Count, or the MapReduce word count. And we define this mapper. So this Mr. Job class has a function, mapper, and we overload that function. If you don't know enough object-oriented programming to follow what I'm saying, that's fine. You just need to have an idea of the syntax here. If you follow that syntax, you're okay. So the idea is you program these two functions, mapper and reducer. And the mapper gets a key and a line. And then for each word in that line, so this split here splits at every space. So we get the whole line of text, we split it at every space. That gives us the single words from that line. So for each word in that line, I now give out the lowercase version of this word and a 1. Remember, my goal is to count words. So what I'm doing here is, it's the same as here. This mapper here is going to put out A1, A1, B1, B1. Actually, it's not going to be A, but B is going to be bus. So some type of word. So this is yielding all the different words it has seen, and the value is always 1. So for each word that is encountered by a mapper, it's going to produce one word value pair. That's a lot of pairs. That's all I want to say. And then here's the reducer, and that takes now the word and the number of occurrences. Now these are a whole list, right? Now we're down here. The reducer already gets a list here. It's going to get bus, 1, 1, 1, 1, as many ones as there is the word bus in the text. So the reducer gets the word and a list with all the occurrences. So all we yield now is the word and the sum of all the ones. And we have counted the words. If you do not understand any line of this code, please speak up now, because the rest of the lecture is going to be hard if you don't. Yes?
So what's the input? You have to input a tax or website or something. So where do you input that?
So the question is, where's your input? And here I only showed you the code. So again, the framework does that for you. When you do Mr. Job, you specify the input, which in my case, I'm going to show an example. It's just a text file. You could also load a web page. Yes. Okay, seems to be pretty clear. So here's the example that's going to show you the input. So green eggs and ham. I actually did not know this children's book, but I think every native English-speaking child out there most probably does, and a lot of others as well. So the whole book goes, I don't like green eggs with ham. It's like, here I am, Sam I am, I don't like green eggs with ham. And it's Dr. Seuss, and it's actually the result of a bet. He wrote his first bestseller, and then his publisher said, I bet you cannot write another bestseller with only 50 words. And he won. No, Dr. Seuss won, because it's the 4th best-selling English language children's hardcover book of all time. Not just of a particular year, but of all time. And it's only using 50 words. And we're going to verify that. So this is the beginning of the book. It's like, I am Sam, Sam I am. And it's like this dialogue, and he says where he all does not like green eggs and ham, and you see this repetitive structure, which children really like, and that enabled him to only use 50 words. So this is our input now. You can put this in a text file, and then pipe that into your script. And what is going to happen then here, this mapper here is going to get one line of this file per call of this function. So the key is going to be undefined. It's 0 or an underscore or something. Might be the line number, but we don't care that much. We care about the line here. So this text file goes in, and the first mapper sees I am Sam. And then for this line here, it calls the split function with the space delimiter, and does the for loop over the single words. So this for loop now is going to go over I am Sam. And for each word then, I output the lowercase version of that word in 1. So it's a lowercase I, 1, am, 1, Sam, 1. So each word of the sentence is going to generate one key value pair. And the reducer then is going to see for each of these single Sams here, it's going to see a 1. So the reducer down here, for example, now looks at word and occurrence. So word, it's all the different keys it had seen. All the different keys are all the different words that are in this text. So it's going to see Sam, and then a 1 for each occurrence here, because for each occurrence of the word Sam in this text, the mapper outputted one key value pair. Right? So this is this idea of thinking now. You need to think about what is your key and what is your value. And in this case, it's actually very simple, right? Your value is just 1. So all the magic is in this shuffle and sort phase that the MapReduce framework actually does for you, right? That's why this works. If I don't have the shuffle and sort, I would be stuck with a lot of key value pairs. But the shuffle sort is going to sort them all for you and aggregate all the different ones, so that in your reducer, you only have to sum them up. So if you want to use Mr. Job, this is how you do it. So I said no IPython notebooks, unfortunately. So you have to put your script into a Python file. And then you run normal Python. You call Python, give it your script. And here's where the input file comes in. And you pipe that file into your script, and the output goes into a TXT file. This is how you call Mr. Job. So in this then, what an output file looks like. If you actually run this, so you see A is 60 times in this text, M is 16. So you get all the different keys, which were our different words, and the number of times they occurred in the text. And the way to verify that he indeed won his bet is to look at the length of this list. So there's actual data science you can do, even with such a simple, silly example, right? It's just a Hello World example, but there's a really cool TED Talk about culturomics. What they did was they did this word count on all of Google Books, right? It's for large data sets. That's a really large data set. And you can go to this web page, the Ngram Viewer, and you can enter whatever word you want and the time frame, and it's going to show you the frequency with which this word occurred. And you can see I put an apple here, and 1860, people were not that interested in healthy nutrition, whereas 1980, something really happened and people got really healthy. Right? So apples were all the rage, and still are, right? Most probably it's going like this. So they called it culturomics because you can see censorship in these graphs. You can see how Jewish authors go down in Germany in certain times, for example. You can see other political movements, war, just the mentioning of war in newspapers and books, right? You can see peaks during the world wars. So it's really, it's such a simple thing to do, but because they were able to crunch this really large data set, it's cool data science. So another example, just to teach you this key value pair thinking, because this is also going to be useful for a lot of Spark applications, is an anagram finder. So an anagram is words or phrases consisting of the same letters. So an anagram of dormitory is dirty room. You're just allowed to take all the letters and you rearrange them to mean something else. So election results, an anagram is lies. Let's recount. So we can use MapReduce to verify anagrams. So we're going to give it dirty room and dormitory, and we want to know, are these two really an anagram of each other? And the input file is one word per line. So we already have a set of words that we want to test. And here's the whole idea. So now there's the mapper, and that again, same as before, gets a key that we don't care about, and the line of text. So now we make a list out of that line, and we sort that list. So this assumes that those words are already cleaned, right? We assume that there are lowercase and all of this. So this example is not dealing with the cleaning part, showing you the main parts. So you make a list of this line, and you sort the letters. And we said there is only one word per line. So what I get here now is actually all the letters of the world scrambled and sorted by alphabetical order. So what I have here now is a canonical representation of the anagrams. That's what they all have in common. That's the main thinking here. Because this is using the same letters. If I strip this down to just the letters and sort them by alphabet, if one is an anagram of the other, they're going to be the same, right? So this is the way you have to think about your problems. You have to find the important keys and the important values that solve what you want to do. So now we yield the sorted version of the letters in the word and the line, which was the original word. So I have the original word as the value. Before we only had number values, there is no restriction on this. The value returned does not have to be an integer. Actually, it can be a whole dictionary if you want to. And then you give it all the different letters, which is the canonical representation. And then you have the reducer. So now here we get the key, which is just the same. We don't care so much. The important part about this key was in the shuffle and sort, right? What the shuffle and sort did, it gave us a list now of all the anagrams, because they all had the same representation by the sorted letters. So this reducer now here doesn't care about the scrambled alphabetical order presentation anymore. It's just caring about the list of words it gets. So, and now we just list those together and look whether the length of these anagrams is greater than 1. And if it is, then these are actually anagrams of each other. If that list is just 1, it was a word in our whole list that was not an anagram of any other word in there, because it was the only one producing this key, this sorted sequence of letters. And I'm going to close here. And then we can do a bit next Thursday in the beginning. And then Rahul is going to take on from there and talk with you about Spark, which is actually MapReduce kind of 2.0. So get into this thinking idea of key value pairs, please, and have fun.